Hello everyone, and thanks for watching Edupedia World videos. This is the second video for the topic of bar magnets, and in this video we'll learn about the magnetic fields and the magnetic potential created by a bar magnet. So before that, there's one small thing in the previous video I forgot to mention. We saw that U is equal to minus m dot b, and this was true assuming U is equal to 0 when m is perpendicular to b, and that makes sense. M is perpendicular to b means m dot b is 0. That also means for any other value U is negative, and U is minimum when m dot b is equal to m into b, or when the angle between them is 0. So the important point here is that U is minimum, or the dipole is most stable when m is parallel to b, right? And this is also true for electric dipole. So whenever you keep an electric dipole in an electric field, it will try to rotate until it's parallel to the electric field, because that's when the potential energy is minimum, minus p dot t. Whenever you put a magnetic dipole in a magnetic field, it will rotate because of the torque until the magnetic field and the magnetic dipole are parallel to each other, and that will be its most stable state, right? So let's get back to a bar magnet. So first we'll see again in this particular video many similarities between electric dipoles and magnetic bar magnets. So first of all, what we'll do is we'll take a standard bar magnet. It has I'll just draw them at the ends just for the sake of clarity, but they'll be a little bit inside, and 2L is the magnetic length. Also, just we need to remember that the magnetic length is 2L. That's something which sometimes students forget, and it ends up creating a factor of 2, and that's a problem. And the magnetic dipole moment is equal to 2ml, right? M times 2L. Now first we'll try to calculate the electric field at an end zone position, that is on the axis, then at a broad zone position. But to calculate the electric field at a random position will be slightly tricky, because electric fields are vectors, and it will be mathematically slightly more complicated. So then we'll introduce the idea of a magnetic scalar potential, just like an electric scalar potential. Then we calculate the scalar potential at any point, and from the scalar potential, by differentiating, we'll be able to calculate the field, and that will be much easier, and we'll see the advantage of using concepts like scalar potential. See, when I teach, I know there's a certain number of concepts we need to teach, but it is nice to show students why those concepts make things helpful. You could easily solve every problem in electrostatics without using the concept of electric potential, but it would be much harder. Electric potential makes things easier. That's why we study it, right? So minus m plus m, they're a distance 2L apart. We'll just take a distance d here from the center, right? And we'll calculate the magnetic field at this point due to this magnetic dipole. So that's easy enough. Calculate the magnetic field due to each of them and add it up. So the magnetic field due to this one will be towards the right, and it will be mu naught by 4 pi m by r square, right, towards the right. The magnetic field due to this will be towards the left, minus mu naught by 4 pi, sorry, this is not r, yeah, I'll just write this as r plus and r minus for now. R plus is this distance, r minus is this distance. Then we'll write those values. So it will be mu naught by 4 pi m, that is common, 1 by r plus square. R plus is d minus l, right? So 1 by d minus l whole square, minus 1 by, now this is d and this is l, so d plus l whole square. And now you see why it was better to take the total length to be 2L, because if we took the total length to be L, then we would have ended up with L by 2 and L by 2 everywhere, and it's nice not to have fractions, because that reduces the chances of making errors, right? So we'll just simplify this, and what will it give us? Mu naught m by 4 pi, this will be d square minus l squared whole squared, basically d minus l into d plus l whole square, and above what we'll get is d plus l whole squared minus d minus l whole squared, so that will give me 4dl, right? And we know that 2ml is capital M, so it can be written as the magnetic field is equal to 2ml will be capital M, so mu naught by 4 pi 2m d by d squared minus L squared whole square. Right, so this is the magnetic field at an end zone position. But right now we have, this is by the way called the end zone position, just like in electric dipoles. Right, but this is the actual field. We have not yet used any approximations. Now we'll use the approximation, and just like in the case of electric dipoles, here the magnetic dipole approximation will be D is much greater than L. Right, so actually we're looking at maybe a plus and minus magnetic dipole, and we're looking at the magnetic field somewhere here. So the distances between these two don't really matter much, and in that case we can actually ignore L squared in front of D squared, and the final result we'll get after the approximation is B is equal to mu naught by 4 pi 2m by d cube. Right, and also we can put the vectors because the direction of magnetic field is towards the right, and the direction of this dipole is also towards the right. Right? This is very similar to the formula we had for electricity. In electricity we had the formula electric field at its end zone position is 1 by 4 pi epsilon naught 2p by d cube. Here we have mu naught by 4 pi 2m by d cube. Now I'll try to make it very clear, but sometimes you might not be able to see by handwriting. So make sure you know the difference between small m and capital M. Right? All these are capital M. This is small m. I'll just try to write small m like this for now, like this. So this is small m, this is capital M, right? And this is the relationship between the two. So we see that for an end zone position, the magnetic field is exactly what we would expect if we were to create a mathematical model that mirrored the model of electric field. Let's look at the broadside zone position now. Yeah, so let's say this is 2L minus M is here is plus M, and we would like the magnetic field a distance d away from the center. Right. So what we'll see is we'll calculate the magnetic field due to each and add them up. So the magnetic field due to capital M, not capital M, sorry, due to positive M will be in this direction, and its magnitude B positive will be mu naught by 4 pi m by r squared, but r in this case is d squared plus L squared. Right, r squared is d squared plus L squared. This is B plus. This will be B minus. B minus is equal to mu naught by 4 pi m by d squared plus L squared again. So the resultant magnetic field, these two components will cancel and these two components will add up, so that the resultant magnetic field will be 2 into mu naught by 4 pi m by d squared plus L squared into the cos of this angle, and this angle is the same as this angle, and the cos of this angle is L by root of d squared plus L squared. So L by, and this becomes to the power 3 by 2. Right, and then what we can do is we can use the approximation, and L square can be neglected in terms of d square, assuming d is much greater than L. From that we can get the magnetic field to be, and 2ml I'll just write it as capital M, so mu naught by 4 pi capital M by d cube. Right, and this is exactly by what we would expect, because for the electric field we had mu naught 1 by 4 pi epsilon naught p by d cube. There is a factor of 2 for the end zone position. There is no factor of 2 for the broadside position. Right, and actually if you were interested in doing a little bit higher mathematics, I would suggest you try to calculate the magnetic field at any random point a distance d away at an angle theta. It will depend on two things, d and theta. Right, I try to calculate it, and I'll show you the answer after calculating potential, and you'll see that it comes more easily that way. So first what we'll do is we'll define the concept of a magnetic scalar potential. And we'll exactly mirror what was done in electric fields. So we'll say V of R2 minus V of R1. the difference in two scalar potentials is equal to minus the work done from R1 to R2 by the magnetic field. Right, and when we take the VR as VR minus V infinity, that means we've taken V infinity to be 0, and in that case it will be minus integral of infinity to R, I just put vectors here, B dot dr. And again, from this particular equation we see the standard similar definition to electric field. The definition of magnetic scalar potential is the work done in bringing a unit magnetic charge from infinity to a particular point. Right, work done by us. Work done by us in bringing the charge slowly will be opposite to the work done by magnetic field. That's why there's a minus sign. Right, and from this again you can get the three standard results which we got for electric field as well. Bx is equal to minus del V by del x, By is equal to minus del V by del y, and Vz is equal to minus del V by del z. So if we know the potential as a function of x, y and z, we'll be able to calculate the field in any direction. Again, for a single charge, just like electric fields or electric potentials, we'll have V of r for a single point charge, mu naught by 4 pi m by r. I'm not going to derive it, it's easy enough. This is mu naught by 4 pi m by r square dot dr, and it'll come quite easily. Right, so this is the magnetic potential due to a single charge, and it is just like the electric potential, which is 1 by 4 pi epsilon naught q by r. Right, so this is for a single magnetic charge. Now let's get back to the problem at hand, calculating the magnetic scalar potential and from that the magnetic field at any random point due to a dipole. We'll still use the dipole approximation, but it will not be just a broadside on or an ends on position. Right, so this is minus m, let's say m, this is 2l, this distance let's call it r, let's call this theta. What is theta? This is the angle, this is the direction of magnetic dipole moment, this is the direction of the r vector. So theta is the angle between m and r. So now we'll make some constructions, and it's not very clear from the figure actually. Yeah, so that's why I probably should draw a proper figure. Just 1 minute. I want to draw a figure in which you can really visualize the dipole approximation, and this is the same approximation that we've used in the electric dipoles, so you should be familiar with it. Yeah, so we're calculating the field at a point very far away, right? This distance is r, the middle one, this is theta. This hole is 2l, so this is l and this is l. Now I'll construct perpendiculars here, and we can sort of assume that from this point, from point A to O, should be equal to BO, right? Because this is 90 degree, this is almost 90 degree, this is sort of like an isosceles triangle. So this distance OB can be written as OA, and OA is, let's say this is OA is OP minus PA, right? So let's call this R plus, because this is plus and this is minus, and this R minus. We can see that R plus is approximately equal to D minus L cos theta, and R minus approximately is equal to D plus L cos theta. If I take this to be C, then CO, let's say, I'm just naming these variables randomly, so QO can be taken to be equal to PO, and CO minus CQ is QO, and CQ is equal to L cos theta, right? So now after we've done this, we can easily calculate the scalar potential here. V r theta will simply be mu naught m by 4 pi 1 by d minus L cos theta minus 1 by d plus L cos theta, right? Because they're in the opposite direction. This magnetic field will be, this scalar potential will be positive due to plus m, this will be negative due to minus m. What this gives us is, this is equal to mu naught m by 4 pi. Now in the denominator we'll have d square minus L square cos square theta, but we'll just write that as d squared, or r squared, sorry, this should be r. So in the denominator I just write r squared because I'll assume that L cos theta is much smaller than r, which is the dipole approximation. In the numerator we'll have 2L cos theta. Right, and 2ml can be written as capital M, so we get the final standard answer. V at an r theta is equal to mu naught by 4 pi capital M by r squared cos theta. This tells us the magnetic scalar potential at any point which has coordinates r and theta. From this we can actually calculate the magnetic fields as well. There will be one magnetic field BR along the radial direction. There will be another magnetic field B theta along the tangential direction. So BR will be minus del V by del R, and that will be so this will be r to the power minus 2 r to the power minus 3, so it will be mu naught m cos theta 2 mu naught m cos theta by 4 pi r cube. Right, and we can see if theta is 0, then it will be the ends on position, and this gives us the result we've already derived, mu naught by 4 pi 2m by r cube. Right, also b theta. Now here some people might make the mistake and say minus del v by del theta, but theta does not have the same dimensions as r, and if you change theta by a small amount, this point will move here, but the distance moved will actually be r theta, not theta. So this will be minus del v by del r theta, or minus r del v by del theta, because theta is the only thing that is changing. So this should not be del v by del theta, this is del v by r del theta, because this has to have the dimensions of length. So del v by del theta will be cos theta's derivative will be sin theta, and there's a minus sign, and we'll divide by r, so we'll get a cube. So it will be 2 mu naught m, sorry, there will not be any 2, mu naught m sin theta by 4 pi r cube. And if some of you would like to calculate magnetic fields from the previous method by taking magnetic fields individually and adding, you should try it. It will be slightly more complicated mathematically, but this will ultimately still be the final answer. Right, so this completes bar magnets, and what we've done in bar magnets in these two videos is, first of all, we've created a hypothetical model for magnetic charges which mirrors the model for electric charges. That makes a lot of mathematics easier because we've already solved many similar formulas for electric charges. Then we took a current carrying loop or a magnetic dipole and we replaced it by a bar magnet which has a south pole and a north pole, or a negative and a positive magnetic charge. Then we calculated the field and the potential at any point. Field first we calculated for ends on and broads on position, but then now we've calculated the potential at any point, and this gives us the fields at any point. So pretty much our study of bar magnets is complete. Also we've learned that the torque on a bar magnet is m cross b, and the potential energy of a bar magnet is equal to minus m dot b, and that means the potential energy is minimum when m is parallel to b. So magnetic field tends to align all magnetic dipole moments towards itself. In the next video, we start our study of the magnetism of the Earth, which is also called terrestrial magnetism. Thank you.